Electromagnetic waves are one of the greatest miracles in the universe. Our cat already took cover, not because of the spectacular meaning, maybe rather because today there are no wires to play with. However, I think it is worth to know more about wave propagation. We are going to examine the radio range from 1 meter to some kilometers, which is of interest for many of us. As usual, I'm trying to make things easy to understand. And of course, there will be spreadsheets that can predict wireless range. The list of wireless systems is almost endless. I just want to mention the most important ones that we can tackle with our methods. There is Wi-Fi, Bluetooth, Zigbee, DECT, LTE, 5G and others, which appear in applications in everybody's life. Hobbyists and future experts know even more systems like LoRa, ham radio systems, license-free radio, etc. In case we want to apply a radio system, usually the first question is about the range. We can read about range records, which generate often far too high expectations. Sometimes we find suppliers' information about the typical range. However, it doesn't answer the specific questions that you have. Can I reach the basement from my living room in the second floor? Can I get a suitable indoor signal in the neighboring building? Can I cover my property area with the system? We will introduce some methods and tools that will give answers here. First, we look at free space wave propagation, which can be directly derived from the law of nature. Then we will add the penetration loss through walls and obstacles to our model, because this is our problem in 99% of our scenarios in the range of less than 1 kilometer. Above 1 kilometer, we apply the so-called Hata-Okumura model, which was derived from professional measurement campaigns. Finally, we need to talk about signal statistics, since radio signals are usually volatile. Let's start with the easy part. For this method, normally we should be completely in free space. However, scenarios like the given one are coming very close to it. We can apply the law of nature to calculate the received signal strength that we get in a distance. And by the way, this is perfectly described in Wikipedia, in case you are interested in more details here. For the calculation, we need to know the frequency and the effective isotropic radiated power of the transmitter. The rest is easy mathematics, as you can see from the formulas that I provided on the bottom. As long as the received power is higher than the receiver's sensitivity, we can assume that the radio system will work, provided that there are no interfering signals or timing limits. Well, this is no rocket science, however, I felt it would be good to have this in a spreadsheet. So, whenever you want to know where the physical limits would be for a system, you can make up your own mind with that little tool. But it can do a lot more, as we will see. Let's demonstrate the tool with a Wi-Fi example. We want to know how far we could get with a 5 GHz Wi-Fi signal under free space conditions. Okay, we need to insert the 5000 MHz here. The transmit power from the router is 20 dBm in theory. However, our devices are often weaker because they have no proper antenna and they want to save battery power. Therefore, let's assume 10 dB instead of 20. Our receiver sensitivity can vary between -90 and -70 dBm. A really decent and stable Wi-Fi link we can expect at -72 dBm. Now, by increasing the simulated distance, we find that we could reach a bit more than 50 meters, provided that there is no interference from neighboring networks. Next, we demonstrate a LoRa link, which is an interesting narrowband system for low data rates. In our case, it runs at 866 MHz. The transmit power is 0 dBm, which equals only 1 milliwatt. The receiver sensitivity is -118 dBm, and a stable connection we can expect at a minimum at -109 dBm. We increase the distance to 1 kilometer, 5 kilometer, and even in the end 8 kilometers seems possible. Interesting. With 2 orders of magnitude less power, we can achieve 2 orders of magnitude more range. What a difference the bandwidths can make. Here is a third example for the use of the tool. We want to estimate the effective radiated power of a LoRa transmitter. It shall be in a distance of 3 meters from the receiver. You get a received power level of -40 dBm from the reported RSSI of your receiver, or you get it from a field strength measurement device. We inserted the 3 meters distance as well as the correct operating frequency. Then we adjust the transmit power until we get the -40 dBm isotropic received power. This corresponds then to something around 0 dBm. Of course, this indirect method is not very accurate. However, it is not bad for a no-cost method, and it is often sufficient for the hobbyist. In an earlier video, I applied a self-made RF measurement device which is more accurate. I will explain how to build and use it in coming episodes. Next, we look at the short range with some obstacles in our way. I call this the usual scenario for wireless systems around buildings. Our signals need to propagate through walls, windows and vegetation. Usually, these obstacles are causing a significant attenuation for our signals. And therefore, we need to consider them in our equation, because they can reduce the radio range really dramatically. An easy method to estimate the obstacle attenuation is also given in our tool here, which I will show you in a minute. We go back to our 5 GHz Wi-Fi example, but this time we consider a brick wall with -17.63 dB attenuation. Now the maximum range goes down to 8 meters instead of 50. And in case we consider 2 walls, the range even goes down to less than 2 meters. This means that it is almost impossible to establish a stable link at 5 GHz Wi-Fi through two thick walls. In case we use 2.4 GHz instead of 5 GHz, we have to consider only -15 dBm per wall. We would get then -74 dBm in 5 meters distance, which would be sufficient. I think many of us made this experience with Wi-Fi in reality. I need to talk a bit more about the obstacles attenuation that came just out of the blue here. The given table is derived A, from my own experience with wave propagation, and I'm using here 2.4 GHz as a reference, and B, from the fact that wall attenuation is frequency dependent. For the input fields, you can insert any frequency within the range of 200 MHz up to 10 GHz. In case you have better reference values for your local circumstances, you can insert these instead of mine. You can also choose another frequency for your own reference. In case you are even more sophisticated and you have two references at two different frequencies, you can also adjust the A value so that the table will fit to both of your reference tables. Let's take another interesting example with LoRa. I explained several LoRa scenarios in the last episode. Here is now a new one. I did a range test in the field with my little LoRa project. In this scenario, the receiver is on the balcony of our flat. The wave propagation conditions were not ideal because the signal path was obstructed by a few trees. Just as a hint, Google Earth Pro can help you a lot with such problems. Besides the height profile, you can analyze also obstacles with this. Here is my analysis for a far point that I could reach with my signal. Cool, isn't it? In fact, you can see some trees that are in the way of our propagation path here. We can now calculate something interesting with our tool. By computing with the FreeSpace tool, we get a prediction of -92 dBm field strength. The difference to the measured -105 dBm is 13 dBm, which must be the loss from the trees. Knowing this, we can calculate a realistic maximum range under the given conditions. It would be close to 2 kilometers with -109 dBm received power. By comparing the number of trees and adding some dBs accordingly, we could also estimate the range in other directions. The summary of part 1. We gave some insights into wave propagation and we discussed some relevant scenarios for the short range. We predicted the received power and the range. We also explained the way how to adjust the wall attenuation according to other measurement references. The coming part 2 will cover mid-range prediction models and the coverage probability. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.